The third type of plate boundaries are transform plate boundaries. In this case, the plates involved grind and slide past one another without creating nor destroying any new lithosphere. Okay? But nearly grinding their edges together, creating some friction and some resulting in sideways, like movement that is sideways of the plates, one going one way and the other plate going another. So this is sort of the motion that they would have. Maybe. Okay, just sliding past each other, sometimes creating friction, but no new crust being created or old crust being destroyed. So these type of plate boundaries account for, again, about 20% of all plate boundaries in the planet. Divergent and convergent plate boundaries each accounting for about 40%. And most of them occur in the ocean floor. Most of these transform plate boundaries occur in the ocean floor. Here they offset segments of the oceanic ridge system, producing a step-like plate margin. So if you guys remember the oceanic ridge system, that's the system that occurs due to divergent plate boundaries, and it was that belt that was 70,000 kilometers in length. The transform plate boundaries, for the most part, just act by offsetting this ridge system sideways. So let me see. So if you see, transform plate boundaries are outlined in green. So for example, here in the southern Pacific plate, as it's moving away from the Antarctic plate, you're seeing that the divergent plate boundary is not a perfect continuous ridge system, but rather it has been offset in a step-like way, as you're seeing right there. So that is the motion that these transform plate boundaries have. Okay? An important transform plate boundary that you guys all know about happens right here, and we'll talk about it in a second, in the next few slides. Okay, so many times these transform plate boundaries are called transform faults. And as I said before, they are very common in offsetting the mid-oceanic ridge, in which case they are also called fracture zones. Okay? The term fracture zone includes the active faults as well as their inactive extensions into the plate's interior. Okay, so it includes active faults, and we'll cover that when we cover earthquakes in the chapter, as well as the inactive extensions into the plate interior, meaning faults that are no longer undergoing this amount of seismic activity. So the transform faults also let us see the mid-ocean ridge being connected with subduction zones, such as it occurs in the Juan de Fuca plate, as you'll see in the next image. So there's a very famous transform boundary that we have, and I already gave it to you in that slide. It was meant to be a surprise. But if you had any guesses, that's the San Andreas Fault, which occurs in California right now. So this is one of the ridges where you can see the fault's action pretty well in place. So if you look at this feature and this feature, they used to be connected once upon a time. So if this is where the fault lies, which is pretty much how it goes, this is the motion of the two different plates. The one on the left, which is the Pacific plate, is moving northwest, and then the one on the right, which is the North American plate, is sort of moving to the southeast in reality. So as I said in the previous slide, for this image that you're seeing here, you can see the Juan de Fuca plate located in the Pacific Ocean and having the three types of plate boundaries within it, having a fracture zone which separates and grinds the Juan de Fuca plate and the Pacific plate, and at the same time being subducted underneath the North American plate. So remember, from the three types of boundaries, again, divergent, convergent, and transform, that as they act all throughout the Earth, they cancel out in mass, okay? Also, something important to keep in mind is that the Earth's surface area is fixed. So the boundaries that each plate has with another may change through time, and that the face of the Earth itself may change with time, but that the Earth will remain in mass balance, unless there's an addition of mass through like a meteorite impact in which case the amount of mass that is added is not great anyways. But overall, the amount of mass must remain nearly the same in the Earth's surface, so that surface area is not changing, and that's why the creation and the destruction of overall mass by these plate boundaries must remain in place, or I should say in balance. All right, so having covered those three different types of plate boundaries and the three types of convergent plane boundaries as well, now you have an idea of what are the motions that are going on Earth. So the size and shape of the different plates change with time, that we know, although Earth's total surface does not change. For example, plates like Antarctica and Africa, which are both surrounded mostly by divergent plate boundaries, are currently growing. But in contrast, if you take plates like the Pacific Plate or the Philippines Plate, that are surrounded mostly by convergent plate boundaries, therefore, and hence are being subducted, they are losing size for the most part. So some plates get completely subducted, in fact, as happened to the Farallon Plate that got subducted underneath North America on its west coast. So the Farallon Plate has the same motion that the current Juan de Fuca Plate was having, so it was subducting underneath North America, and it kept being pushed towards North America and subducting underneath it, and so it got subducted all the way underneath it. And if there is a remnant of the Farallon Plate, it would now be sitting kind of underneath, if I'm not wrong, like Montana and the Dakotas or so. So the breakup of Pangaea is a great example of the changes that occur constantly with the different plates. Through different geologic tools, scientists have been able to reconstruct the chronological events that occurred for Pangaea to break up. So Pangaea was the supercontinent which had all current continents pretty much together. So the sea surrounding Pangaea was called Pantalasa, and a small section separating the Horn of Africa with the Arabian Peninsula attached from Eurasia was the Tethys Sea. So you might have heard the reference to the Tethys Sea, and the remaining of the Tethys Sea currently is pretty much like the Mediterranean Ocean as we know it. So the northern part of Pangaea, as it split, was called Laurasia. So that would be pretty much North America and Eurasia minus India right now. And then the southern part of Pangaea, as it split, was called Gondwanaland. And I think you saw an image of Gondwanaland earlier in the slides as well. So Gondwanaland included Antarctica, South America, Africa, Australia, and India, pretty much. Okay, and again, that's where, for example, Wegener took a lot of his fossil correlation work as evidence for his hypothesis of continental drift. So the first thing that happened in the rifting of Pangaea was rifting that started about 200 to 190 million years ago and resulted in the splitting between North America and Africa about 180 to 150 million years ago in the Jurassic period. So this created a new ocean basin, which is the current North Atlantic Ocean. About 130 million years ago, the South Atlantic began to open near the tip of what is now South Africa, and this migrated northwards at the same time as it was kind of rifting, eventually opening up the whole Atlantic Ocean from South America. Further breakup of the southern landmass led to like the separation of Africa and Antarctica, and sent India on a northwards journey about 100 to 90 million years ago. So you see in the images all the things that I'm telling you. So you see that about, again, 90 million years ago is when India starts going up northwards. Okay? By about 50 million years ago, Australia had separated from Antarctica as well, and the Atlantic was a full-fledged ocean because now South America and Africa were also a part, not just North America and the northwestern part of Africa. India also eventually collided with Asia, which is thought to have begun about 50 million years ago and created the Himalayas and the Tibetan highlands. About this time as well, Greenland continued splitting from Eurasia, which completed the breakup of the northern landmass, so the breakup of Laurasia. During the past 20 million years or so, the Arabian Peninsula, or the Arabian Plate, I should say, split from Africa through the Red Sea. Baja California has separated from Mexico, and the Panama Arc joined North America and South America to produce our current globe's appearance as we see it today. So in the past 20 million years ago, not that much has happened in terms of large changes, but you still see the transition of certain parts of our globe's geography as we see it today. So if current trends continue as we know them today in terms of plate motion, in about 50 million years, the Baja Peninsula and a portion of California will have slid past North America, and LA and San Francisco will actually pass each other in about 10 million years. So again, that's because of the large transform fault that occurs there, that San Andreas fault as we know it. And if you think about it, in about 60 million years or so, it will begin, like that southern bit of California and the Baja Peninsula will begin to collide with the Aleutian Islands in Alaska. So the motion of the Pacific Plate being subducted by the North American Plate and the Eurasian Plate is fairly fast for this to occur in 60 million years. So also in 50 million years, Africa will continue to move northwards, eventually colliding with Eurasia, which will close completely the remnant of the once Tethys Sea. So it will close the Mediterranean Sea. Australia and New Guinea will move north and move towards Eurasia, towards a collision with Asia. It might not have collided by 50 million years from now, but it's going to move further up north and be much closer to what it is right now. Also, North America and South America will begin to separate from each other, and the Atlantic and Indian Oceans will grow, and the Pacific Ocean will shrink. So the map that you see up above is that idea of what will happen in 50 million years from now. The one that you see below is a representation of what the world could look like in 250 million years from now. But of course, for this specific map, there are many more assumptions that occur, and we won't get too much into the details of this map's prediction, such as South America and Africa, for example, being next to each other again, even though the Atlantic Ocean is currently growing. So we won't get too much in detail, but if you are curious and you want to know more, definitely look it up and also let me know, and we could chat about it. All right, so in the next few slides, what we'll cover is going to be the evidence for plate tectonics that differs from the evidence from continental drift hypothesis. We'll also cover how the motion is measured nowadays, what are the different ways in which we can do that, and finally we'll cover the hypotheses out there towards what is driving plate motions. So again, those are currently just hypotheses, not theories, but they're somewhat well accepted amongst the scientific community. So let's jump into the evidence for plate tectonics.